LinkedIn used keyword matching for matching queries with user profiles until recently. They've now moved to fully AI-powered jobs and people search. And what's more interesting, they've published comprehensive details of how they implement the architecture for both high accuracy and high throughput. So let's try to understand what does it take to go from simple keyword-based search to fully AI-powered search, uh, neural networks, transformers-based search at the scale of LinkedIn, and get optimized for both getting highly accurate results as well as handling millions of queries per second. So this is the architecture here, and understanding embedding based retrieval and then re-ranking. The standard pipeline for vector search comes, they have a router which which distinguishes between precise queries or ambiguous queries. And precise queries are routed to the traditional keyword search, while ambiguous queries go to the this pipeline, which is enabled by vector search and language models. So there's a lot of meat in how they've created this efficient pipeline, and how they have created data, uh, rated data at scale, and there are huge efficiency improvements. First thing that I do is assign labels to those queries, and those labels are used as signals of intent. And then the query passes into the standard dual tower, where query and documents are both embedded, and the closest matching documents are found. In this case, the people profiles, for example. And then a small language model ranks the retrieved candidates. So for the embedding encoder, they generate a bunch of features based on the document, and they compress that into a single vector and keep some high level features like the job profile title uh, um, as separate features, and that gets encoded into a single vectorized single vector, and that's further optimized, and I'll talk about that later. And that goes into the language model, which is trained by on a multiple objectives. It's a multi-teacher distillation. So they take a large language model, a bunch of large language model, each of them tuned on, for example, the clicks. They trained it on both the click data as well as the job applied data. There are different large models, 7 billion parameter models for each of those, optimized on each of those signals. And what they do is they use these multiple teachers to train a single small language model, which is less than a billion parameter size. And the model learns about these rich, nuanced probability signals. And the digital model also captures the reasoning capacity while remaining lightweight. Key contribution they have capture the accuracy or the signals more deeply by using multiple teachers, and then combining the outputs of the teachers together to train the small language model. The small language model is highly much more efficient, as well as captures the multiple properties of multiple teachers very nicely. This diagram shows in more detail there are a couple of teachers. There's a much larger 7 billion model, which is relevance LLM based on product policy. That is distilled into a smaller relevance teacher. And then again, there is a 1.7 billion multi-task LLM teacher for the actions that the users have done: jobs apply, dismiss job, view the job, and people, the connections, and looking at profiling. So all these two LLMs capture the actions, member actions, and the relevance of the documents. And both of them together are distilled into the ranker as well as the retrieval model. So nice, interesting that the ranker and the embedder are trained jointly. The idea is how they have cleverly used LLM judges to label documents at scale, millions of documents, while always keeping it aligned with the human judgment, or what the human annotators think program managers think what queries and documents are relevant. So first, the program managers generate a bunch of examples documents defining the policies which say when is a query relevant to a document. Okay, so they get an internal annotator alignments. All of them align on these policies with kappa greater than 0.8. They take these policies and filter them further down and give it to LLM Judge as a prompt. And those are used by the judge to label new queries and documents. So this ensures the agreement alignment with the humans. The judge doesn't give arbitrary scores. It's always aligned based with these policies, and this gives a nice rating LLM, but it's not scalable, so it's further distilled down for high throughput. Pipeline work efficiently at runtime, handle huge amount of millions of queries per second. They perform a bunch of optimization. So first, they prune the model. They remove the feed-forward layers that are irrelevant and make the model small. The most clever contextual optimizing they do is about context pruning. So using the full job descriptions as part of the context is the job description are essential for giving a good match, for giving high accuracy. But if you include the whole of it, then that fills up the 90% of the context, and they have a 2K token size. So that prevents adding more relevant information. So the key idea that insight they had is that we can summarize the job description into a smaller paragraph, fewer tokens, and then embed that separately as a single vector. Yes, and reuse that vector directly when we're doing re-ranking. So this summary-based contextual pruning is the amazing insight that they have to scale the re-ranker model while keeping it precise. Finally, they have a single pipeline. They have jointly trained the embedder and the re-ranker. So they have a single pipeline that does efficiently computes the embeddings, few tokens per item, add some other features. For example, the title of the job, company name, location, or the member name, and these are separate features along with the job description embedding. The whole pipeline or whole architecture in one glass. There, it's easy to understand it if you split it into the feature generation part, the retrieval part, and the ranking part. Now, in terms of improvements, they get over 75x improvements in the inference speed because of these optimizations. If you just use the SLM with the raw text, the quality in terms of NDCG was 0.9432. Throughput was very low. With the pruned SLMs format and the summarized embedding, they could increase the throughput almost 10x, while a slight drop in the quality. And with finally the embedding compression of the summarized text, they were able to scale it to 10x further. So recap, how did they build? How do they scale semantic search system to link it to the scale of LinkedIn traffic? I think there are three key ideas. One is that they were focused on a small re-ranking model, building a small re-ranking model that, in spite of being small, captures the signals from multiple large teachers, which individually capture different kind of signals like clicks or user actions. And then they build a quality evaluation framework using an LLM Judge. LLM Judge can give arbitrary scores, so they ensure that they align with human judges by curating examples, making the human program managers grade those examples, and then sampling those examples in a nice way to train this LLM Judge. This LLM Judge could enable the quality scoring in real time. So that's the second thing, a good quality eval framework. And finally, deployment optimization, model pruning, and context compression. very smart technique to compress the context so that a small language model could handle traffic without losing the accuracy. So that's how LinkedIn managed to scale semantic search to search as well as people search